Hello, this is a continuation on our notes of evaluating limits of other indefinite forms. In class, we reviewed the forms infinity minus infinity, as well as 0 times infinity, and we showed how we can rewrite these limits using algebraic manipulation, that was dividing by the reciprocal, or getting common denominators, to get it into the form of 0 over 0 or infinity over infinity. This is useful because we can now apply L'Hopital's to evaluate our limit. We have 3 more indeterminate forms for you today. That is 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. You might be thinking, Mr. Smith, 1 to the power of anything is 1. Well, like that guy in the video said, infinity is not a number, it is a concept, and 1 to the power of any number is 1, but infinity can represent, it's more of an abstract idea here. It is not just necessarily one single number that we can evaluate 1 to the power of at. And likewise, we don't know how to treat 0 to the power of 0. What is that number to the power of itself when itself we think represents nothing? How can something be to the power of nothing if it itself is nothing? As well as infinity to the power of 0. So, when we get these forms in our limits, we need to use logs to move the exponent down and then exponentiate our answer at the very end. Think back to implicit differentiation, when we would have equations like y equals x to the power of x, and we didn't have derivative rules. We know the power rule when we have x to the power of some number, and we know some logarithmic rules when we have a to the power of x, how to take those derivatives. When we had x's in both the base and the exponent, we had to take the natural log of both sides in order to differentiate using implicit differentiation. We have a slightly similar process here. We're going to have to take the natural log of the function inside of our limit. So here's the general idea. If we're given the limit as x approaches some value a of some function u of x, then what we can do, right, and if this evaluates to any of these 3 indeterminate forms with these exponents here, then we can take the natural log of this expression and also raise it to the power of e, so e to the power of the natural log, and these 2 statements are equivalent because e's and natural logs are inverses. There's a property that says that this holds true. This is useful because with limit properties, we can actually rewrite this base here of e and our limit of the natural log of u of x all inside of the exponent. This is something that we can do with limit properties. So this is essentially saying, hey, if we've got an indeterminate form with a 0 and we've got some infinities and such in the exponents here, in our u of x, we can take the limit of the natural log of this u of x, which will help bring that exponent down into a more workable form. We can evaluate that limit, probably following this rule right here, where we had 0 times infinity, manipulate it into a usable form to use L'Hopital's, find the value of this entire limit, and our answer will be e to the power of that value. It is super, super important that you do not forget to exponentiate at the end, that you don't just find this limit of the natural log, because that is different than the limit of the actual function itself. Without e to the power of that limit of the natural log, these are different values, and we're not even answering the question anymore. We gotta raise e to whatever power of the value that we found. So let's do an example of this. Buckle up, this is going to be a long example, but it is extremely important in calculus. So let's dive to it. This is at the heart of calculus, folks. We are taking the limit of this function right here as x approaches infinity. Let's go ahead and try some direct substitution by plugging in infinity for our x's. And we're going to get 1 plus 3 over infinity, all raised to the power of infinity, which gives us 1 plus, 3 over infinity is 3 divided by a huge number, which is 0, with our limit. So 1 to the power of infinity, which is indeterminate. Indeterminate. Because this is one of those 3 indeterminate forms with the exponent, then we know that we should take the natural log of this function. So I'm going to go ahead and label the inside function as u of x equals 1 plus 3 over x, all raised to the power of x. This means that when we take the natural log of both sides, the natural log of u of x equals, I'm going to already bring my exponent down when I take that natural log using my properties, x times the natural log of 1 plus 3 over x. Now, this function here, this natural log function, is in a more workable form that I can better take the limit of as x approaches infinity. So, this means that the limit as x approaches infinity of the natural log of u of x is equal to the limit as x approaches infinity of all of this jazz, x times the natural log of 1 plus 3 over x. Let's try some direct substitution here. When we do direct substitution, we're going to get infinity times the natural log of 1 plus 3 over infinity, which is infinity times natural log of 1, which is 0, which is an indeterminate form. And this is an indeterminate form that we studied in class, just like infinity minus infinity, that we can algebraically manipulate now to get into 0 over 0 or infinity over infinity. I believe I highlighted this in blue. So let's go ahead and rewrite this limit. We had infinity times 0. So I'm going to take the x and I'm going to divide by its reciprocal over 1 over x. And let's see now, is this in a condition where we can take L'Hopital's rule? Yes, we get 0 over 1 over infinity is 0. We can use L'Hopital's. So let's go ahead and apply L'Hopital's. And you need to give yourself a lot of space for this one, okay? So I'm writing my limit far below. I'm going to move my screen so I have lots of space for these derivatives. The derivative of the natural log function is 1 over the inner function multiplied by the chain rule piece. What is the derivative of 1 plus 3 over x? Well, 1 plus 3 over x is equivalent to 1 plus 3 times x to the negative first. So that derivative is going to be negative 3 x to the negative second. All of this divided by the derivative of 1 over x. So that's x to the negative first. That derivative is negative x to the negative second power. Look at that. These guys divide to 1, as do those negative signs. So ultimately, we are left with the limit as x approaches infinity of 1, let's multiply that 3 up. 3 over 1 plus 3 over x. Gorgeous, 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 gorgeous. Can we evaluate this limit? Yes, we can. Let's plug in infinity. We're going to get 3 over 1 plus 3 over infinity is 0 total. So our answer is 3. Done, right? Wrong. No. Okay. 3. This means, so, the limit as x approaches infinity of the natural log of 1 plus 3 over x, all to the power of x, equals 3. We want to find the limit of just 1 plus 3 over x, all raised to the power of x. So to undo that natural log that we took in the very first place, we need to raise e to the power of each side. AKA in formal, all serious math language, rewrite this into exponential form, which is going to give us, let's go ahead and move that e into the inside of the limit. The limit as x approaches infinity of e to the power of the natural log of 1 plus 3 over x all to the x equals e to the third power. The e and the natural log undo each other. So this limit here is equal to e to the third power. This was a lot of writing, folks. Let's zoom out. Whoa! Okay. So these are all the steps that show you like how and why this all works. I would like for you to still write your substitution and that you are determining the limit of the natural log. The reason why I want you to write these steps is that you know exactly what you're doing. When I was doing calc back in college, like I would just have kids, student athletes, take the natural log. They're just like take the limit of the natural log and then just do e to the power of whatever it is at the end. I want you to write this U substitution so that you know exactly what you are finding. You do not, however, need to write these last steps here, where I break down like how this is all equal to e to the third. If you would like to, once you found that last value of 3, skip to this last step, that therefore the answer is e to the third, then you can do that. One last example now. We've got a right-hand sided limit of the following function. As usual, let's go through and use direct substitution. We're going to get 0 to the power of the natural log of 2 over the natural log of 0. Now, because we are approaching from the right-hand side, we're really taking that natural log function. I want you to think of this graph right here. And as we're approaching x values closer and closer to 0 from the right-hand side, our natural log is heading towards negative infinity. So this limit is approaching 0 to the power of the natural log of 2 over negative infinity, which is a 0 to the 0th power, essentially, since infinity is a huge number and you're dividing the natural log of 2 by a huge number. So this says, okay, we need to take the natural log of this function here. Let's let u of x be 2x to the power of the natural log of 2 all over the natural log of x. Take the natural log of both sides and bring down that exponent. Awesome. Let's determine the limit as x approaches 0 from the right-hand side of the natural log of u now. I'm also noticing here that we've got a fraction times natural log of 2x, so let's go ahead and combine into one fraction, so the natural log of 2 times the natural log of 2x all over the natural log of x. Let's see if direct substitution is going to help us out today. We're going to get the natural log of 2 times the natural log of 0 over the natural log of 0. And those natural logs of zeros are really approaching 0 from the right-hand side here. So thinking about our graph, these will both give us negative infinity. So 2 times negative infinity over negative infinity, which is essentially infinity over infinity. This means that we have grounds to use L'Hopital's. So let's take that derivative of the top function. The derivative of the natural log is 1 over the inside function times the derivative of the inside function, which is 2, times that natural log of 2 that was already there, all divided by 1 over x. So these x's are actually going to divide to 1, as will 1/2 and the 2 up there. So we get the limit as x approaches 0. Oh, from the right-hand side, don't forget that notation there, that's important, of the natural log of 2. Now, that right-hand side notation is important because if we think about the natural log in the very, very beginning, that function, the limit only exists from the right-hand side because this function is not defined from the left-hand side or at x is equal to 0. So the limit as x approaches 0 overall of the natural log function does not exist. It only exists as we approach it from the right. So it's important that you write that plus sign in all of your work. All right, what is the limit as x approaches 0 from the right here? Well, no matter what the x value is, that limit is going to equal the natural log of 2. So we found out that the limit as x approaches 0 from the right of the natural log of 2 to the x raised to the natural log of 2 over the natural log of x is the natural log of 2. This means, therefore, the limit as x approaches 0 from the right of plain old 2x to the power of the natural log of 2 over the natural log of x must equal e to the natural log of 2, which is just 2. So this was another case of one of those indeterminate forms, exponential indeterminate forms, where we must, there we go, where we must take the natural log, manipulate using algebra, use L'Hopital's, and then exponentiate at the very end. All right, well done, folks. I will catch you next time.